So the key thing with these energy methods is that the energy going in also has to be equal to the energy coming out. So we have a beam which is fixed at one end, and it comprises a vertical section and a horizontal section, which has a load of 20 kilonewtons being applied to it. So it's 4 meters tall and 3 meters long. It's made out of steel, so that has a modulus of 200 gigapascals and a second moment of area of, this was 297 by 10 to the 6, and I gave that to you in meters per hour. If we want to get that obviously into meters, to convert that, to go to millimeters to meters, you divide it by 1,000. Because we have 4 of those, we just need to divide it by 1,000 times. So that is 297 by 10 to the 6 by effectively 10 to the power of negative 12. Because that's, you're doing 10 to the negative 3, you're doing that 4 times. So we get 10 to the negative 12, so that's just 297 by 10 to the negative 6. And what we're wanting to do here is to find the deflection delta. I'm going to give it some delta at B. Now, the key thing here is that because we're looking at the energy being input by this force, you can only look at the deflection in that same direction, the deflection that is generating work. Because it's an energy-based method, you can't look at other directions that aren't generating work. You can only interact with the deflections in the directions that are generating work. And similarly, you also can't look at the deflection here, at this point here, because there's no force being applied there. Therefore, even though there is a deflection there, there's no force being applied there, so there's no work being generated there. There's only work being generated at that point in that direction. So if you look back at, we had all these, where these came from, the fact that we could equate the strain energy here, we also use this one, so stress. So if we can have a formula which tells us the stress throughout the volume due to a particular loading, so this is the stress area energy, that is equal to the input energy. Here we have force times displacement, but you can also have moment times rotation, just a force, and that has to be the same location. And we're equating those two things, so we're equating that value, and we're equating this value. If we can come up with an equation which tells us what stretch you're getting due to that loading being, or whether it's a moment, throughout the whole volume, you can just chuck it in there. And so we can do that for obviously a beam and bending. We have M1 and I. And if we can get M as a function of X, it's pretty straightforward. So this is what we get here. We get this equation here. So that's where that comes from. And the reason why it's M squared is because that was stress squared. So we can use that. So what we want to find here, and this deflection is at the deflection at any point where you're loading it up. Here we just have one beam, but you could have any sort of beams. Doesn't have to be limited to this. So that's what we're going to make use of. So we have half times by the force applied, which is that 20 kilonewtons. That's point B, so that's the force at B times by the displacement at B. is equal to the strain energy, and the strain energy is the integral basically over the whole volume of, yeah, let's do all of that for a moment, of the moment squared divided by 2 EI, and we need to do that over the whole volume. For us, we can simplify that because we're going to know what the forward moment is in the direction x, so we can simplify this down to being equal to just integrating it along the length x over distance x. So we're just going to do it along these lengths and lengths of it. So what we want to come up with is things that now. It might be a little bit confusing at the moment because we essentially have 2 different sections. You can, like, if I just, fix this section here and I had it fixed here, this would be fairly obvious. What's really causing a little bit of confusion is the fact that we have that second section and the second section is looking a little bit different. So that's fine. Key thing here is because it's an integral is just like a sum. Well, that's what the integral sign is it's a big S for sum. So we can independently, we can do the integral, the sum of this one, and then we can do the integral, the sum of this one, and then sum those 2 things together. And that's it. So we want to, if I call this like section 1, this section 1. We want to do the integral of this section first. So the moment in section 1 squared divided by 2 EI, and we're going to do that, or if I call this like distance x here, I'm going to call it x1, and we're going to do that over distance x1. And obviously it goes from the start of x1, and we're going to go for all those 3 meters. So we're going to go from 0 to 3. And then we also, so that's just doing that section, but we also need to do this section here. So we need to account for strain energy in that section. So we're going to add on, do the same sort of thing. This is going to be section 2. We're going to put in an x coordinate for that as well. x2. So we're going to find the moment in section 2 and square it, and divide that by 2 EI. We're going to integrate that through the value of x2. And we're obviously going to go from the start of that to the end of it. So we're going to go in section 1, we're going to go from the start to the end. Section 2, we're going to go from the start to the end. This just goes from 0 to 4 meters. And that makes it, that's probably the most difficult thing in this, understanding how to break that one. And you often need to do that, like, if you didn't, with our previous example, when we had all those pulleys and we had to divide up into different sections, we used them with pulley brackets. Like, if you had any reason to create a new function for n, you need to do the integral multiple times anyway, because you can't integrate a discontinuous function. You can do integrals with those McCall brackets, but you have to structure it. Cool. So things we need to do now. Like, I know E, I know I, I've got E and I common. I know the value of 2, it's 2. So we just need to find the values of M1 and M2. So find M1, M2. Can we do that like we always have done? So we have here 20 kilonewtons. This is obviously for section 1. We have a distance x1. It will have a upwards shear and a clockwise moment. Trying to find the value of the moment. So we'll just take some moments about that point there. Okay, nice and easy about this point here. As we have done, so that makes it nice and easy, so we don't have to figure out B. We don't need to figure out B anyway, because it's not necessary. We're trying to find out 1 and out 2, so let's do some of the moments at about that point. Shall I say equals 0? So this value here is negative because it's going counterclockwise. Counterclockwise. And this one's also going counterclockwise. It's also going, oh sorry, it's going, this one's going clockwise. This one here is also going clockwise relative to that point. So that is also minus 20,000 x1. So we can say that m is simply negative 20,000 x1. We can do something for section 2. This section is a little trickier. I want to draw this. I'm going to draw it. Yeah, let's draw this. So we have a load of 20 kilonewtons here. If you think about it, this has been like sort of rotating the other way, so my shear force would go that way. This will still go that way. That's it too. It's just that this distance now is 3 meters. That's next to. So we can do some marks there. Again, we'll do it at this point. So this is going negative, so negative m2, and then this is just relative to that point, that's also going negative. So it's going to be 20,000 and this time the distance that's going by is not x, it's not related to x at all, it's just the value of 3 meters. So here we have that m2 is simply just negative 60 kilonewtons. Oh, sorry, negative 60 kilonewtons. No matter what value, as we change the value of x, like that distance and that force is still the same. So the moment, the internal bending moment is still the same. Yep. Why? So again, well, I didn't draw it down, but I took it x going this way, but y going that way. So sorry, x, y, and z. The z is still coming out of the page. So my z is still counterclockwise. Z positive. Counterclockwise is all because the z-axis is coming out of the page. Then when I wrap my fingers around, they go counterclockwise. So. What's the question? that's not showing me the positive direction of Z. That's just showing me the direction that M2 is acting on that part of the body. So it's just saying that, well, if M2 was positive, it would be acting that way on the body. Okay, so we found M1, M2, it's fine, we can go back up and we just need to put them in here. It might seem a little tricky, but it's really not that hard. So we have... not for this one, but in general, in the other cases, yes. It won't be for this one because it gets squared. So negative squared x. But for other cases, if you use it for methods, then yeah, you could get it wrong. It's mainly sort of thing. It's not. It just means like. Sorry, I'll say it this way. The only thing it really affects, if you get it wrong, the worst thing is you say that the top side or the deflection is going in the wrong direction, or like once the wrong side's in compression and tension. That's the worst thing you can get. You're not going to numerically get the wrong value. So we bring these down so we have. They both have 2 EI up front. That's constant. It doesn't change. The cross section of the material doesn't change. So we'll bring that out as common factor up front. So we have 1 on 2 EI. Then we just need to go into this. Oh, sorry, we're doing that. So M1 is negative 20 about 3 x1 squared goes from 0 to 3 plus M2, which is just negative 60 times 3 squared dx 0, 4 dx. They're pretty easy. These once we square it, these are constants. We can take that from. So if I'm going to do the square first. I'll do the square. So 20 squared is 400, or negative 20 squared is 400 also. So 400 by 10 to the power of 6. Yeah. And then I have x1, so to integrate that, we raise the power and we divide by that. Yes.
M1 refers to the vertical beam, right?
Horizontal.
Horizontal section.
Yeah, so that's this one. So this one.
Okay. Horizontal means the top one.
Yes.
Okay, then M2 is
Vertical. Is that okay?
the M2 over there looks like it's the top section on your horizontal.
So that's the second one. Yes. What am I doing wrong, sir?
The sketch you gave.
The sketch?
That's M1. Okay, so the bottom drawing is the vertical one.
Bottom drawing is correct.
For the vertical section.
Yeah, this is for the vertical section.
Okay.
Because it's increasing with x2. So we have half x1 squared, and that goes from 0 to 3. We get a value of that. We do the same thing over here. 60 60 squared is what? 3,600. Plus 3,600, and then that goes. That's a half. Oh no, half. Sorry, because there's no thing there, so that's just x2, and that goes from 0 to 4. Yes, I did. I did basics. We know what the value of E is. We have I and E is 200, so we can just solve for that. Pretty straightforward. 1 on 2 by 200 to the 9 by 297 by 10 to the negative 6. By 10 to the 6. 9 squared, sorry, 3 squared is 9, divided by 2 is 4.5, so that's 4.5, plus 3,600 by 10 to the 26, and let's just toss up 4. That 10 to 6 gives that 10 to 6. Just makes it easy for you as well. I had a number, but I don't necessarily trust it, so we'll just take that off the next one. Oh, sorry, one thing. Sorry, I made a mistake there. This, so this is x squared, so this should be x cubed, means to be divided by 3, which just means that will be 3 to the power of 3 is 27 divided by 3, which is 9. So that will be 9. We get a value for that? Yes? This one? Because when I was taking the integral, there's no, which we're taking the integral with respect to x2, and there's no x2 inside of that. Yeah. So it's just a constant gradient. Any answers? Okay, 151.5. What units would that be? What have we calculated here? This is the internal energy, yes? This is the strain energy. So remember what it was we were saying the work done on the system is equal to the strain energy. So if this is energy, what's the unit of energy? Joules. Because we've used all SI units in joules. But we do also know that that's equal to half the load times deflection. We're looking to find deflection. What's this? So this is just going to be 1 to 5, 1.5 divided by things in that one which are tricky. Like initially when we faced the problem, it looked problematic. But the really useful thing about energy methods are they enable you to look at sort of because they deal with energy, which is a scalar value, they allow you to deal with sort of really sort of black box systems, like more complicated systems. You don't get as much information out of them. But for a system like this where like you can't really do this using the previous method that we utilised, where we took the integral of m twice and did it that way. You couldn't do this method, but because we're just doing an energy-based method, we can use it to find out that deflection of that location. So what we did was we started off with our equation and we just said, oh, okay, if we need to do it over all lengths, we just need to find, we know what, through the whole system, we know what I is, we know what E is, we know what 2 is, we just need to find values or equations for M over the whole length. And then, so that was the first thing, and then the second trickiest thing probably is just doing these free body diagrams. This one's easy, this one's a little bit more tricky, something you know. The rest of it is once we've got that, like getting these equations or getting these is fairly tricky, or going from this to this is pretty easy. And then it's just a matter of chucking in here, making sure you don't make any mistakes like that. I want to get up through. I want to get up top. That last bit's very easy. Okay. If you got a question, ask a question. Okay. So that's what you all did for homework. I know every single one of you did that. That's fantastic. Thank you so much. Make sure your answers are correct, just like mine. Yes, okay. So we do that. Today, the rest of what we want to do today is we want to go through this section here, which is should be pretty easy. Pretty straightforward. There's a couple of things. We'll do like one practice from here, but it's pretty easy. It's very similar to what we did last time around. But I do want to go over a couple of like more interesting points in that as well. We'll do that. We'll do the question. We can have a break, and then we'll come back and do the start of the fluid section. That's what we're going to do for tonight. And we're going to do a few fluids problems. So we did stress transformations, but we also sometimes want to do strain transformations, and we want to look at how systems behave in different directions in strain. So we said that with stress in 3D, we needed 6 different values to fully know the stress state. Stress XX, so on the x-axis in the x direction, stress YY, stress ZZ, also known as stress or sigma X, sigma Y, sigma Z. But then we also need to know on that X face, what is the stress in the Y direction, what is the stress in the Z direction, so tau XY, tau XZ, and we also need to know tau YZ. If we know all those, then we can, in any orientation, we can figure out what all the values are, and then we can use those stress transformations to look at what the stress is in any other direction. The ones that we looked at yesterday are fine if you want to operate in 2D. Go from 2D to 3D is pretty easy as well, because you just do it this way and then you do it the other way. And then you can orientate yourself in any 3 dimensions. Just like that with strain, with strain, if you want to know the full 3-dimensional strain status of an object, of an infinitesimal, you need to know the strain in 6 dimensions, the same 6 dimensions. So how much is the x face moving in the x direction, how much is the y face moving in the y direction, z face z direction. So that's epsilon x, y, z, as well as how much are they shearing, which is essentially like an angular deformation. So how much is the X phase tilting in the y-axis? How much is it tilting in the z-axis? So how much is the X phase tilting in the y-axis? How much is it tilting in the z-axis? How much is the y phase tilting in the z-axis? And with all those, you can figure out strains in any three directions. Now, talk about this a little bit here. Generally speaking, for us as mechanical engineers, a lot of the time the stuff we deal with is three-dimensional behaviour, but probably an equal amount of systems we deal with are two-dimensional, which means that all the things of interest for us occur in just a single plane. So you can imagine, if I'm working on the ship here, all the stress, all the deformation is going to be on the plane of this sheet. There's not a lot of interesting things happening in this direction. But that's fine, and that enables us to make simplifications in how we analyse that system. But this is still a three-dimensional object. Just because we can, like, the things of interest are only occurring in those two dimensions, it doesn't mean it's not a three-dimensional object. So we do need to make some assumption about what's happening in that third dimension. There are a number of different ways to get around it, but the two most prevalent cases you could do is you could either say there's no sort of force in that z direction, or there's no deflection in that z direction. If there is no deflection in that z direction, so if I pull and push this and I move it all around, we don't want to break it. So I could do all the stretching and straining and putting loads in this XY plane, but if there's no deflection in that z direction coming out of the page, then that means there's no strain in that z direction. Right? So that means that all of the strain is occurring on the plane, on this XY plane, this plane here. So that case where there's no deflection in that z direction, that's known as plane strain, because all of the strain occurs on that plane. If we have plane stress, on the other hand, plane stress occurs, plane stress is when we have zero force in that direction, or zero load, I'm going to say, actually. Zero load in that z direction. So what that would mean is we're not, like when I go and make manipulations to this planar surface, that there is no sort of force or no restrictions coming in this z direction. So nothing that's going to impart a force in that z direction. Obviously that means that the z direction is allowed to displace to do whatever it wants, because there's nothing restraining it in that z direction. If that's the case, then that means all the load, all the force, all the stress actually is occurring in that plane, and so all the plane is occurring all of the stress is occurring in that plane. So that's the plane stress condition. So plane stress is when you have all the stress occurring in that XY plane. Plane strain is where you have all the strain occurring in that plane. Why would, if I was pulling this and stretching it and doing all that sort of stuff, why, if I'm putting all the loading in this plane, what would be the reason why there would be any deformation? Like thinking about, I guess, the plane stress case, we're saying that there's no force in that z direction, there's no load occurring in that z direction, but there might be some deflection. What would be the reason for the deflection if I'm loading it up, purely, I'm just putting forces in that XY plane? Why would there be any deflection in that z direction? What's the cause of that? You know Poisson's ratio? Look, have you? Are you familiar with words? Poisson's ratio? Yes? Yeah. A little bit? Essentially, and this is for a little bit later on, but like, when you go, if you've had like, if you've said like, when they like forge metal, right? You can squeeze it that way and it'll expand out the other directions. So I'm applying the load vertically downwards on it, and it's causing it to expand out in the other directions. So a force in this, let's call this the x-axis, is causing expansion in the y and the z-axis. Generally speaking, materials want to try and mostly conserve their volume. The measure of how much it conserves its volume, so it maintains the same volume, or it, as I squeeze it, this measured how much does it squeeze out the other two dimensions. That's measured by the Poisson's ratio. And you can see that here with these equations. So, if I have force in the x direction, if I have stress in the x direction but no stresses in the y and z, then the strain in the x direction is just stress divided by Young's modulus. But for these ones, so strain in the y, so how much is it deforming in the y direction? I have 0 y stress, I have 0 z stress, but I do have some amount of x stress. So that's 0, this is 0, this is some value. It's multiplied by Poisson's ratio, and therefore you can see that we'll have some value of strain in the y. Keen to note, if x is positive, that means the strain in the x direction is positive, but if x is positive here, because of this negative sign, it means the strain in the y direction is negative. So remember that example I gave of like crushing an object, right? We have a negative stress in the x direction, so we'll get a negative strain, but we will get a positive strain in the y direction. Just before I go back to the other point, Poisson's ratio can have values between 0.5, so half, and -1. The vast majority of materials we deal with have values somewhere between 0 and 0.5. If it's 0, they're more like foam materials. So if you can imagine if the Poisson's ratio is 0, then we don't get any expansion in the other directions. So when you crush a foam, it doesn't sort of squeeze out. But metals typically will have, like aluminium has a Poisson's ratio of about 0.3 to 0.33, depending on its grade. Steel is about 0.28. So the closer the value of Poisson's ratio is to 0.5, which is the maximum value you have, then the more, like, if it's 0.5, it always conserves its volume. The volume is always maintained. But if it goes to 0, then the volume isn't maintained at all. You can have negative values, where like, if I pull it in this direction, it will actually expand out the other two directions. These are called auxetic materials, and typically they're like sort of small, like nano materials, very small scale things. Yeah, we don't really deal with those unless you get into materials lines. Okay, so we've shown that like I can stretch and strain it in this x and y direction, and I can have some expansion in z. But that's the only way I get expansion in that z direction. Is if I don't have any like load. If I assume, if it's plane stress, we assume that sigma z is 0. So we have stress in the x and stress in the y, so we're going to have some sort of strain in the z direction. But if we assume that it is plane strain, which means that all of the strain occurs in the xy plane and there's no strain in the z direction, then that means this has to be 0, sigma z has to be 0, and therefore, if we have strain in the x and y, the only way that this can be 0 is if we have some amount of stress in the z direction. So plane strain means all the strain occurs in the XY plane, but you do get some amount of stress in that Z direction. Plane stress means that all of the stress occurs in that Z direction, in the XY direction I should say, but you do get some amount of stress occurring. Or you can have some amount of, you will have some amount of deformation occurring in that Z direction. Now, going back, so that was all the way back. For us as mechanical engineers, most of the things we deal with are plane. Well, if we're going to do our plane stress or plane strain, we're dealing with plane stress. Plane strain typically is when you have things which are clamped. Obviously, in order to have zero strain in the Z direction, you need to have some sort of restriction there to hold it. That can either be like a physical structure that's coming over the top of it and holding it, or if you have something which is really long, then, you know, unless you're right on the ends of it, in the middle, it's essentially like it has zero stress in the Z direction. So that's more like a civil engineering thing. Civil engineers are more sort of plane strain. Mechanical engineers, the structures we're dealing with is more like generally it's plane stress. Right? So most of the things we deal with plane stress. We can use a similar thing as we did, like the same transformations, similar transformations that we did with stress as having to do with strain. The major difference is that now we replace, when we want to rotate and figure out the strain in different directions, we replace tau with gamma xy. So we just measure the strain in different directions. Now, you might think, oh, these are really not as useful. I will tell you, like, if you're like doing experimental work, or if you're doing like in situ engineering, so if you're doing like maintenance things, you're much more likely to use these equations than you are to use the stress equations. That's because you can actually measure strain. You can't measure stress. There's no like stressometer you can put on something. But you can get strain gauge. You go to strain gauges. They're basically little bits of a resistive wire that when you pull them, they get more resistance. And so you can pass a voltage across it, and then you can calibrate them so that you know, like, because the resistance is changing, the voltage, or there will be a voltage drop across it. So you'll know that you can measure the voltage drop across it, and you can calibrate and say, like, okay, if I put this much strain in it, this is what the voltage is going to be. If I put zero strain in it, this is what the voltage is going to be. So you can actually go ahead and measure strain, and often what we do, I did this a couple months ago. We were working on some drive shaft components. We weren't doing it X and Y because we were doing it rotationally, so we were doing it like theta and R. But anyway, theta and X, I guess. We measured the strain on a system, and then the direction we measured it in wasn't actually the direction we were interested in, because we couldn't lay them for various reasons. Sometimes you can't lay them up the directions you want, right? And so then we're more likely to use these relationships, the strain measurements, because that's actually what you can measure. And then at the end of it, we can get that, and then we can convert that back into stresses. But you can actually measure directly strains, which is why these are used. But otherwise, apart from just replacing tau with gamma xy on 2, the reason why it's xy on 2 is because they both contribute to a squishing of it. So there's a bit of shearing on this side, the shearing on this side, you have them together, so it has to be on 2. And we can get these equations. You can do the same thing when you figure out the principal axes. Same equations, again, we're just replacing tau with xy on 2, gamma xy on 2. And you can do the same thing with more circles. The only thing again is that it's gamma on 2, not tau on 2, so exactly the same thing. Yeah, let's just quickly do this one, and then we can have a quick break. and then we'll come back and we'll start with fluids. So here we have put a strain gauge on a component. Looks like some sort of, this is connected to a shaft and we have some sort of actuation. This actually looks like a bike shifter. We've measured the strain in the X and the Y, the shear strain. And we just want to figure out the principal strains and the in-plane shear strains. What's the unit of strain? It doesn't have units, it's dimensionless. So it doesn't have dimensions. So, like, well, here, like, strain is stress is in pascals, non-dimensionless is in pascals, it's dimensionless. The fundamental definition for, like, strain, if you're looking at strain in the X direction, the most, like, familiar thing that the thing you might be the most familiar with is the change in length over length. You might be familiar with that. That is, like, length over length, this doesn't have units. The more fundamental, like this is just an approximate definition. The actual definition I should say, is the derivative of displacement in the X direction, which we say is U, because remember we had U dW. U was the displacement in the X direction, divided by, so how quickly does the displacement in the X direction change as I move in the X direction? So, if I have this pen and I just move the whole thing like 5 meters over this way, that wasn't 5 meters, that was 1 meter. There's no strain in that system in the X direction, because the whole thing, like this point's moving by 1 meter, that's moved by 1 meter, that's moved by 1 meter, that's moved by 1 meter. But if I was to hold one end fixed and then pull the other end, then this end would be displacement 0 meters, and then there'd be a rate of change of displacement as I move in the X direction. And so strain fundamentally is how much the rate of change of displacement the X direction with respect to the X direction, du dx. But that is to say that strain doesn't have the units, it's dimensionless. So this is the one time that imperial units and SI units have the same unit system. Is for strain. But for us, one common thing, for like things like metals, you often end up with things in that strains in the order of like, here we have 250 by 10 to the negative 6. It's a very common sort of value of strain. So you end up with in the tens to negative 6 or to the thousands to the negative 6. So these are commonly referred to as, if I rewrite that out, so we'd have strain in the X is equal to 250 micro strain, where micro is 10 to the negative 6, and then strain is just, so that's more of an engineering unit than like an SI unit. So you'll hear about things booked in terms of micro strains. So this is 250 microstrain, this is negative 450 microstrain, and this is negative 825 microstrain. And we just wanted to, what do we want to do? Find the maximum in plane strains, so that is epsilon 1, epsilon 2, and we also want to find gamma max, and obviously the orientations to that, so we want to find theta S and theta T. So that's just the orientations to those. And that's all pretty straightforward, so we can use like the same equation. So we had with stress, the equation for stress was finding principal stress was, remember, you had the average plus that hypotenuse term. So we had the same thing here. We have the strain 1, 2 is equal to the average normal strain. So that's strain the X plus strain the Y divided by 2. And then we have plus minus the hypotenuse. So we have half the difference. So strain X minus strain Y divided by 2 squared. And then previously we had tau xy, but now we have tau, instead of tau xy, we replace that with gamma xy divided by 2. It just has that divided by 2 term. So we have gamma xy divided by 2 squared. These are all going to be microstrains, so I'm just going to keep that microstrain to the side. So we have 250 minus 450 divided by 2 plus minus 250, well, plus, I guess, because it's minus the negative. 450 divided by 2 squared plus negative 825 on 2 squared. This is just going to be negative 100. I believe. Negative 1, 2. Did you get it? This is negative 100. Is that negative 100? Plus minus, I don't know what this is going to be. So I guess 700 and 350 squared. Plus. So I'm going to guess it's going to be about 480. by 40. 540. Yeah. 41. 541. Okay, so just remember as well that yes, we'll do it this first. So firstly, strain 1 is when we take a positive. So if we take a positive, we get 441 microstrain. When we take the negative, we get negative 641 microstrain. Now keep in mind this is like of a larger magnitude, a bigger magnitude than strain 1, but because this is the more negative term, it is strain 2. It is the minimum strain. It's the most negative possible strain you could get. It asks us to find out the average stress, the average strain. This is the average strain, so the average strain is negative 100 microstrain. And it also asks us to figure out the gamma max. Gamma max is just this value here, so that's 541. The last thing we want to do is just figure out the angles. So tan to theta p is just previously it was like tau on 2 times the difference, but now we're replacing tau with gamma on 2. Oh, sorry, it was 2 tau, and now so what we get is just gamma xy on strain x minus strain y. So that's going to be like negative 50 degrees. Oh, sorry, we don't care about that. We care. Oh, sorry. If we divide it by 2, then theta was like negative 25 degrees, I guess. You can do that because you know that tan of 1 is 45 degrees. And this is a bit bigger than negative 1. It's like negative 1.1. It's a bit bigger than 45 degrees. It's negative. Huh? I said 25. That was ridiculous. What do you say? Negative 24. 24 point. There you go. And then obviously theta s is just that. You can do plus or minus, so you can do plus 45 degrees or minus 45 degrees, you get the same thing. We'll just do plus because that gets us closer to 0. So that is, I can't do this. So that's 20.2, is it? Yeah, 20.2. Okay. Orientation. These are the orientations. So to get the orientation where we have stress 1 and 2, we rotate by that many degrees. And at that angle, obviously, the shear strain is 0. If we rotate it by this many degrees, we'll get to where we have maximum shear stress, that value. And at that location, your strain in the two normal strains will be negative 100 microstrain each. Yeah. You got a question? You got a question?
You explain why it's 45 degrees.
Oh, Yeah. Just because I said it is. It just like was. If I have this, imagine this is a square. If I rotate it 90 degrees, like the strain in this direction has just become the strain in that direction. And so like, if I rotate it 180 degrees, then the strain in the x direction just becomes the strain in the x direction again. But if I rotate it 90 degrees, the strain in the new x direction is just the old strain in the y direction. So every 90 degrees of rotation, you just get you get back to the same thing. So we said it was you can read this from here. Negative 24.8. So I went like this. Hang on, I got to do this right. Yeah, we went negative 24.8 degrees. If I rotated it 90 degrees from there, so I've got direction 1 and direction 2, strain 1, strain 2. If I went 90 degrees, I'd just have strain 1 and strain 2. Right? If I go halfway between the 90 degrees, that's where you get your maximum shear strains. So instead of going 90 degrees, you go 45 degrees, that looks to be exactly 20.2 degrees. And so that's where you would have the average strain there would be negative 100. The average, well, strain that way would be negative 100. Strain that way would be negative 100. And that's the shear strain is where your maximum is. Sorry. You can directly calculate it if you want, but when you go, you can play around with the mathematics in here, and you can show that, or you can see that these two are just opposite each other, and they have a negative. Right? And the reason why it's 90 degrees instead of 45 degrees is because you have 2s in it. Right? So tan, the inverse of the tan is offset by 90 degrees because we have the 2s, that's why it's 45 degrees. So there's the mathematical description, and the paper is like the physical description. Okay, let's come back a bit before 8. So it's currently quarter to 8.